Alright, we're going to go ahead and take a look here at a somewhat basic related rates problem. Now, related rates is always kind of a scary topic for a lot of calculus students because it's a word problem and so forth, but try and explain it in a way that'll break it down, hopefully in a way that can help you solve these problems. So let me just read the problem first, make sure all the words are clear. It says the radius of a circle increases at a constant rate of 6 centimeters per second. Find the rate of the change of the area of the circle when the radius is 3 centimeters. So, first thing, it's really important when you do a related rates problem to be able to, take the information that's given from the problem, and create certain things. So, there's some steps that you could break it down into. So, step 1, let's say. Okay, these don't necessarily have to be in an exclusive order, but I like to identify, so ID, the variables. I'm going to kind of use some shorthand here. ID the variables. So what are your variables in this problem? Because related rates problems are all about things that are changing. And in a related rates problem, there are going to be 2 or more things in a problem that are changing at a certain rate. Okay, and usually how fast one changes affects the other, and so forth. So in this case, to identify the variables, you want to look what is changing in this problem. Well, I have a circle I'm dealing with, right? And so in this, the first sentence says the radius of a circle increases at a constant rate. So it's telling me that this radius is changing. So the radius, so r, okay, is definitely one of my variables. And I got to think about it, as the radius changes, the circle's increasing, and I mentioned area in here, so the area of this circle is increasing. Okay, so that's going to be my 2 variables in this problem, r and a. Alright, and then, again, it doesn't have to be necessarily in this order, but second step would be maybe to relate your variables with an equation. So relate your 2 or more variables with an equation. So in this case, I'm talking about a circle. I've got a radius, I've got area, so in this case, the way I can relate those is a is equal to pi r squared. You have to have an equation that relates your variables together. Okay? Also, very, very important, let's look at step 3 here, is to take from the problem to see what is given. Okay, what is given? And that is our first sentence. The radius of a circle increases at a constant rate of 6 centimeters per second. So now there's a way to take that sentence and kind of translate it into related rates lingo or notation. Okay, so we're talking about the radius increasing. It's talking about how much it's changing, how fast. And you'll notice the units I put here, centimeters per second. Centimeters are units of distance, seconds units of time. And so what I'm going to say for this is that dr over dt is equal to 6, or 6 centimeters per second. Okay? So I take this sentence and I translate it to that. dr over t represents basically how fast r is changing, the radius with respect to time. Well, it's changing the rate of 6 centimeters per second, so that's describing exactly dr over dt. So the key word in this case, increases. That was a key word. Basically, that increases is a word of saying how fast something is changing. In this case, growing. Now, let's just say it had said the radius of a circle decreases at a constant rate of 6 centimeters per second. Same idea, except you would have put dr over dt equals -6 in that case. But in this case, it said increase. So, put 6. And step 4, what are you asked to find? Okay, what do we want to find in the problem? Like, what's our goal? What's our outcome? So in this case it says find, here it's pretty clear, find the rate of change of the area of the circle. So rate of change is a key word right here. Okay, so basically how fast is the area changing? Okay, so which would be dA over dt. d over dt represents how fast the area changes with respect to time. We want to find that specifically when r is equal to 3. So, that's kind of your, oops, that's supposed to be step 4. That's kind of my initial 4 steps of breaking down the problem into, finding all my given information and so forth. So then from here, we need to kind of get going and think, what you do is you use your equation that relates your variables. That's the next thing you do, because we need to come up with something, we need to figure out what dA over dt is, okay? And we need to probably at some point use dr over dt, which we don't see so far. So how we're going to get that is we're going to take the derivative of this equation right here, a equals pi r squared. So when I take the derivative of that, I use some strange notation here. When I take the derivative of any variable, I initially take the derivative like normal. So when I take the derivative of a, the derivative of a is just 1. Okay, so the derivative of a is 1, just like the derivative of x is 1 and so forth. But then, and this is because of the chain rule, I say that a is a function of time, I multiply times dA over dt. Okay. Now, you usually wouldn't see 1 times d over dt, because 1 times d over dt is just d over dt. 1 times anything is just itself. So I would just probably write that as dA over dt. And then equals, now on the right-hand side here, I've got to be careful with my derivative. Pi is just a constant. Okay, so I want to treat that just as a constant, so I don't want to use the product rule here. So I just take the 2 down and multiply it times the pi. So it's going to be 2 pi, and then I subtract 1 from the exponent of r to be r. But then, since I was taking the derivative of r, I multiply times dr over dt. So whatever I take the derivative of, whatever the variable is, my initial derivative is just normal, the 2 pi r, that's just kind of normal, and then multiply times d, whatever that variable is, over dt. In this case, it was r. So, we have, the derivative that we're going to use to solve this problem. Again, our goal is to find dA over dt. Well, if we've got something here. We know that dr of dt is equal to 6. It says it's constantly 6, always 6. We're looking for dA over dt specifically when r is equal to 3, so I can just plug 3 in for r, and I'll have my answer. So I end up getting that dA over dt is equal to 2 pi times 3, and then times 6. So when all is said and done, that's, see here, 36 pi. Alright, now I should just note what the units are, just in case, say, this is a free response and you needed to put units on this. So, you could look at this a couple ways. You have r, which is measured in centimeters, alright? You have dr over dt, which is measured in centimeters per second. So when you multiply those together, it's centimeters squared per second. Or you can just think, it's dA over dt. Well, area is measured in centimeters squared, time is measured in seconds, so it's going to be centimeters squared per second. So what that means is the area of our circle at that moment, when r is equal to 3, is increasing at a rate of 36 pi centimeters squared per second. And, yeah.